So we have this function. Okay, and it's like this. And say we're interested in starting at a, x equals a, and ending at, say, x equals b. We want to know how the distance of that along that curve, along that arc. What is that distance? And this could be any function f. Okay, any function. So, like we said, we're going to, fortunately, okay, that's better. Okay, so like we said, we're going to break this thing up into segments. I'll draw a different color so you can see it. Segment 1, segment 2, segment 3, etc. Okay? And we'll call each one of those S for segments. So delta S1, delta S2, delta S3, etc. So there could be a lot more than just 3 of them between A and B. But in order for you to see it, I can only fit 3 in there, okay? So what are we going to do? We're going to sum up, remember, sum up as j equals 1 to n is the total number of segments, each of those lengths of those segments. And that would be an approximate curve length. Will it be too short or too long, the approximation? Too short or too long? Too short, because we're cutting the corners, right? We're going in a straight line from point to point, but the curves will be a little bit greater than those straight lines. So when you add all of those segments up together, it'll be too small. But if we take more and more and more of these segments closer and closer, with the points closer and closer together, we'll get to a point where the sum of those segments is indistinguishable from the length of the curve. All right, it'll be so close that it'll be the same. Okay. So how are we going to do this? So we need the length of each of these. We need this delta S. Say we'll use S2 as or S1 as the example here. How can I get the length of that straight line right there? Distance formula, which is based on Pythagorean Theorem. So we're going to make a little right triangle. And for delta S1, we're going to have a delta X1 and a delta Y1. So now we can easily write what delta S1 is, or just, for that matter, delta Sj. So delta Sj by the Pythagorean theorem is going to be, so delta Sj squared is going to equal delta Xj squared plus delta Yj squared. So therefore, delta Sj is square root of. This should be very understandable. And so this is for any segment, right? The jth segment. J goes from 1 to n, where n is the total number of segments. So j is just the jth segment, so it represents all of them. Any particular one or all of them. Okay, and so then we're going to sum all those up, right? So it's going to be the sum of all of these segments, which are the hypotenuse of these right triangles. So this is now the integral is taking form here, right? Because we know the integral is sum of all the little bits. And this is exactly the same thing, sum of all the little bits of segments. Okay, so But we know with an integral we're going to need, if we're going to go from x equals a to x equals b, we're going to need dx as part of the deal, right? So we're going to do a little trick here. We're going to multiply by 1 in the form of delta xj over the square root of delta xj squared. So you should recognize that that's just 1. Doesn't change the value of what we've got because we're just multiplying by 1. Because the denominator is just delta xj, so we have delta xj over delta xj. And so we're multiplying that whole thing by 1. And then what we're going to do is, so now that we've got square root over square root. So we're going to do one big square root with all this stuff inside. Do you see? We'll do one big square root with all this stuff inside, and then it's going to leave our little delta x out here, which will eventually be our dx. Okay? So one big square root with all that stuff inside is going to be delta xj squared over delta xj squared. Plus, and then we're going to have delta y j squared over delta xj squared. And so can I do two steps at once here? Can I make that all one thing squared? And then times delta xj. Just delta xj, which is staying here from the numerator of this. Okay, not bad, right? Again, what did I do? I multiplied by 1, then I grabbed this thing that was square root and I combined it with that and left this out here. And so then this term will go underneath that, and this term will go underneath that, and that'll be delta yj over delta xj quantity squared. Okay, getting close here. So first thing becomes square root of, what's that? 1. Anybody recognize what this is? So delta y over delta x. Okay. So as delta x gets very small, that is, yes, that's the derivative. That's the derivative of y with respect to x. It's the derivative. Some are saying tangent. Yeah, that's what. So yeah, that's the derivative. Okay. So we're going to write it one more time. So now we're ready to say, let delta x go to 0. So delta x is going to get very, very small. And when delta x gets very, very small, this becomes our integral. And we're gonna have it. We're gonna the length of the curve equals integral from a to b of 1 plus the derivative squared dx. And so what does that do? That finds the arc length with respect to x. So starting from x equals a to x equals b, it'll sum up all those little itty-bitty segments, right? Which will essentially be the same as the curve because the points are so close together. The difference between the arc and the segment will be so indistinguishable that adding up the segments will get us the arc length. Yeah, that's the derivative. That's the derivative. Okay, so all the principles involved in that, you should know and be able to reproduce this. This is pretty straightforward. Nice little derivation. Okay?
The only thing I understand is what's the first step.
What's that?
The only thing I understand is how you come up with like the change in xj over square root.
Oh, it just because it works. So you do it because it works. You wouldn't have to figure that out, but just understand what happened, right?
This is like a proof, basically.
There's a proof, yeah. This is proving that this formula calculates the length of curve. Okay, so let's do an example. Other questions on this? Okay, so find the length of the curve. Y equals 1 plus 6 x to the 3 halves, x from 0 to 1. Okay, so we just got our formula here. So we could also write this as y prime, right? dy dx is also y prime, is also, if it's given as a function, f prime. So given that I have y, I'm going to write dy dx as y prime. It's the exact same thing, right? So what do we need to set this up? There's just one thing that we need. We need y prime. We need the derivative, right? It's because the derivative is going to go there. So derivative is 0 plus 9 x to the 1 half, right? So 3 halves times 6, x to the 1 half. Okay, so then our length is going to be integral from 0 to 1. 1 plus 9x to the 1 half squared dx. Question?
On the test, is it a fair game to ask us just to recreate that whole formula again?
Yeah, you should know everything about that. Yep. Yep. Or I could ask you about a part of it. But yeah, the whole thing is fair game. So this turns out to be 1 plus 81x. And that's a piece of cake. How do we do the antiderivative of that? 1 plus 81x to the 1 half, 3 halves. No, antiderivative, not derivative, right? Antiderivative. We're going to need a 2/3. That would be like our first attempt, right? Our first attempt. And then think about taking the derivative of that. We'll also have, by the chain rule, we'll have it times 81, which we don't have here, therefore 1 over 81. Okay? And if you have been clutching to the u substitution, you're more than welcome to. And you'll get the same thing. 1 over 81, 2/3, 1 plus 81x to 3 halves from 0 to 1. And we'll get, what is this? 2 over 243. 82 to the 3 halves minus 2 over 243 times 1. So that value right there, what is the length of this curve if you graphed it, starting at x equals 0 to x equals 1. That's how long it would be right there. Okay, any questions? All right, so let's do something a little more challenging and actually slightly more interesting. So what we want to do now is we want to use this to actually derive, let's derive the circumference formula for a circle. We'll use this arc length formula to derive the circumference of a circle. So first let's put our circle on here. So if I okay. So first of all, we need a circle. We need what is, if we were to write a circle as a function, do we know how to write a circle as a function? Let's see. So we want to make it centered at the origin. That's the easiest. So can we write the top half of a circle? Can we just write the equation of a circle? So any circle, radius r, centered at the origin. What would that equation be? Anyone know? So it would be x squared. So we're trying to represent every point on the circle. So if this point is xy, right? Then this distance here is what? That's r. So we can use Pythagorean Theorem to write an equation that relates x and y, which would be x squared base squared plus y squared equals r squared. Therefore, y as a function of x would be, for the top half of the circle, square root of, so if someone said that before, good. So when we take the square root of both sides with the y, we're going to get a plus or minus. The plus is the top half of the circle, all the positive values of y. The minus would be the bottom half. Okay? So what we're going to do is we'll integrate as x goes from 0, x equals 0, which would be the top up here, to x equals, what's x equal right there? R. So we're going to integrate from 0 to r, and then we're going to multiply that by 4, and that should be the circumference of a circle, which is, what is the circumference again? 2 pi r. Okay, so this is what we're after. We're going to prove, we use the arc length formula to prove that the circumference of a circle is 2 pi r. We're going to do that by doing the arc length for a quarter circle, and then we should get 1/4 of that, right? When we do a quarter circle, what should we get? We should get pi r over 2, 1/4 of that. Okay, so here we go. So we're going to do, again, the integral from 0 to r of square root of 1 plus, okay, derivative. So we got to do the derivative here. So y prime is 1/2 1 over 2, radical in the bottom now. By the chain rule, we also have negative 2x. So it's going to be 1/2 that thing to the negative 1/2, so I just made it a square root in the denominator. And then by the chain rule times negative 2x. That's our derivative of our top half of the circle function. Good? All right, so we're going to square that. And so that'll be nice because we'll get rid of that square root, okay? So we're going to square, oh, and the twos go, right? We'll get rid of that first. So this, when we square that, it gets a lot friendlier, right? We're going to get x squared over quantity r squared minus x squared dx. Okay, so now we got to do some algebra here. So the first thing we're going to do is we're going to make this all one fraction. We're going to add these and get all one fraction underneath the radical. So we got a little work to do here, a little algebra. So common denominator is going to be r squared minus x squared. What are we going to have? We're going to have top and bottom by r squared minus x squared. And then this is just by itself. So it's going to be r squared minus x squared plus x squared. More nice things happening here. Numerator just becomes r squared. Right? Because minus x squared plus x squared is 0. So we're just going to have r squared in the numerator over Okay, and we're really close. So what do you notice in the numerator? We have the square root of r squared, which is just r. Okay, so we can do okay, we actually don't want to do that, and I'll show you in a sec. What we want to do is we want to divide top and bottom by r squared and make this a 1. Okay, that's what we want. We want a 1 there. So we're going to divide the top and bottom by r squared. Okay, so why do we do that? Because it works. Okay? So we're going to divide the whole top and bottom, both top and bottom by r squared. So we're going to get 1 over the square root of 1 minus x squared over r squared. Did you catch it? So we're going to do r squared over r squared at the top. That gives us a 1. Square root of 1 is 1. Then when we divide the numerator by r squared, we're going to get 1 minus x squared over r squared. Do you see it? Ask me.
Why does dx change into dr?
It does not. Okay, so then we're one step away here from something we should recognize. 1 over the square root of 1 minus quantity x over r squared. Who knows their derivatives? What is it? The arc sine. This is arc sine, right? Arc sine is 1 over 1 minus argument squared. So what we have is the arc sine of x over r. But there's going to be chain rule coming back the other way, right? So if we were to take the derivative of this by the chain rule, we'd also have, we would get, by the chain rule, we'd have a times 1 over r, which we don't have a 1 over r here. So we're going to need times r. Okay, and then that's going to be from 0 to r, right? And we're expecting this to be, what, pi r over 2, 1/4 of that. That's what we're thinking. It's going to be 1/4 of that, which will prove that the circumference is 2 pi r. So here we go. We're going to plug r in, and we're going to get r times, what did I go wrong here? Sine inverse of 1. Okay, we'll just go with it. Sine inverse of 1. Okay, and then minus r times sine inverse of 0. I'm scared. What is the sine inverse of 1? Oh, no, I think it's right. Sine inverse of 1, what, is the angle between negative pi over 2 and pi over 2 that would give a y-coordinate of 1 on the unit circle? Pi over 2, right? So it's r. This is sine inverse of 1 is the angle that gives you a sine of 1. What angle gives you a sine of 1? Pi over 2. What angle gives you a sine of 0? 0. Did it work? It worked. And that is 1/4 of 2 pi r. Check. Got it. So we proved that the circumference of a circle is 2 pi r by proving that 1/4 circle is r pi over 2. Yeah.
Why do you multiply by r?
This one?
Yeah.
It's like hold on a sec. It's like undoing the chain rule because we don't just have x squared. We have x over r squared.
Yeah.
So if you think about going backwards to take the derivative of this, you'd have the chain rule, and you'd do the sine inverse, and then you'd have times 1 over r, like the coefficient of x.
Right.
But we don't have the 1 over r here,
So you multiply by r.
so we need the r. So it's like undoing the chain rule.
Okay.
If you're not sure, just do u substitution and start with u equals x over r.
Yeah.
If you do u substitution, you'll do u equals x over r, and you'll have sine inverse of u. But then that r will come out. Okay, so for Wednesday there'll be web work and there'll be a short written portion too. You'll turn in written homework for Wednesday. Okay. Yeah.
This part here, because you're squaring to get rid of the square root, that negative is obsolete, so it's still plus.
Right.
Okay.
Because the opposite or the opposite or its number square, it's gone.
Okay. Just making sure.
Yeah.
Web work? What is quad here?
It is
That's
zero.
What is quad?
It's just a typo or something. I don't know what it is.
Okay.
Just ignore it.
That's what I did, but I was like, maybe I don't know.
No, it was just some weird thing in the code.
Just because you're reaching 0.